Hello students, and welcome to this calculus lesson. In this lesson, we're going to start learning about the fundamental theorem of calculus. In this video, we're going to learn about what it is and how we can use it. So let's get started. So first, let's actually define the fundamental theorem of calculus. First, as long as we have a function f of x that's continuous and differentiable on a to b, then the integral of f of x from a to b is going to be f of b minus f of a. And that capital F is going to be the antiderivative that we learned about in the first lesson of module 6. All right, so let's see how this works. So we have this function negative 2x plus 3. And we're gonna wanna calculate this definite integral from negative 2 to 1. And then we're also going to shade the area of the region that is represented. So as I do this, I have my function here, and we want to find that antiderivative. When you're finding this with the fundamental theorem of calculus, what you're going to notice is that the c's cancel out. So I'm going to actually not write them when we are writing the antiderivatives with that constant, because really when you do a plus and a minus of the constant, f of a or f of b minus f of a, then they're just going to cancel out. So I'm going to leave that off. So as I'm looking at these antiderivatives, it looks like I have negative x squared plus 3x, and I want to calculate this from negative 2 to 1. So I'm going to substitute 1 in here on these x values. So then that's going to be, say, negative 1 squared plus 3 times 1, and then I'm going to subtract it from that lower bound of negative 2. So then I'm going to substitute negative 2 in for x, negative 2. And we just need to solve this. All right, so I get negative 1 plus 3 minus negative 4 minus 6. Okay, so that looks like that's going to turn into a positive. So that's going to be 2 plus 10, which equals 12. So now let's actually find what this area represents. So we're going from negative 2 to 1. So here's negative 2, and here is 1. So if I shade this in, you notice that I really have two shapes. I've got a nice triangle right here, and then I have this nice rectangle right there. So let's see if the calculations actually match up with the geometry of the shape. So that triangle is going to be 1/2 base times height, so that's going to be 1/2. The base is going to be 3, and then the height is 1, 2, 3, 4, 5, 6. All right, so that's going to get me 9. And then let's count up the squares at the bottom. That's 1, 2, 3 squares. So then that's going to be plus 3, which gets me 12. Which notice that these numbers are matching up, because what we're doing with the fundamental theorem of calculus with these antiderivatives is finding the area bounded by the x-axis in that curve negative 2x plus 3. So now let's look at our second example here, where we're finding it from 2 to 5, and what you want to notice is that everything here is going to be below the x-axis. So let's see how that is going to affect the area. So again, we're going to start with, we're getting negative x squared plus 3x, and we're evaluating this from 2 to 5. So let's substitute in the upper bound. So that's going to be negative 5 squared plus 3 times 5 minus negative 2 squared plus 3 times 2. All right, so I get negative 25 plus 15 minus negative 4 plus 6. All right, so then that's negative 10 minus 2, which comes out to be negative 12 in this case. So again, in this graph, we're going from 2 to 5. So let's mark this off. So from here, 2 to 5. And again, if I'm looking at this, I'm looking at it in terms of geometry. We've got a triangle. And remember, everything that's below the x-axis is going to be a negative area. Everything above the x-axis is going to be a positive area. So this triangle, I've got a base of 3. So 1/2, 3 times a height of 6. And so that's going to be 9. And then I have 3 squares right there in that rectangle. So plus 3. And that's going to get me 12, and since it's all below the x-axis, that's going to be a negative 12. So you see that these are matching up. So you can do the stuff above the x-axis, you can do stuff below the x-axis, and you can do stuff like where it crosses over, which is what you're going to see in these next 3 problems. So what I want you guys to do is come do these next 3 problems using the fundamental theorem of calculus, upper bound minus that lower bound, show your work, and see if you get the exact same answers that I do. All right, let's go ahead and review our answers. So in our first one, we get 0, and that's because you notice that the areas of those triangles, using geometry that we have, they're canceling out with what's above the x-axis, and with what's below the x-axis. What's really cool about the fundamental theorem of calculus is that it's going to work no matter what. You don't need to find where those values are going, where the function is going to be crossing the x-axis. You don't need to split it up, although you can. It can help if you need to work with certain functions, or if those functions are changing. But notice here that it's always going to work. In our second problem, we got 4 because more area is above the x-axis. And in our last problem, we got -10 because more negative area is below the x-axis. So let's go ahead and conclude this video by making some of these inferences, some observations from our work so far. So first, we know that the definite integral from a to b of f of x dx is the area of the region bounded by the function and the x-axis. The second thing that we can conclude is that if the definite integral from a to b of f of x dx is positive, then the region bound by f of x and the x-axis is going to have more area above the x-axis than it does below the x-axis. The third thing that we can conclude is that if the definite integral from a to b of f of x dx is negative, then we know that there is less area above the x-axis than there is below the x-axis. And then the fourth and final conclusion that we can make is that if the definite integral from a to b of f of x dx is equal to 0, then we know that the area above and below the x-axis are exactly equivalent. They are canceling out there. And so that's why that definite integral comes out to be 0. Hopefully you did well on those examples. Of course, if you didn't get some of those answers, you can always reach out to me for some help. I'm always happy to help you guys out. Of course, thank you guys for watching. I'm Mr. Hernandez, and this was Mr. Hernandez Teaches.